Presentation of RAPID, design of a modular electrode panel workbench for biosensor prototyping. Presently, the established standards for medical diagnostics are often limited to the bounds of the laboratory, which may present limitations including wait time, lack of qualitative data, costs, and high levels of expertise needed to conduct the test. Often referred to as labs on a chip, point-of-care biosensors use immobilized bioreceptors such as enzymes or antibodies to capture biomolecules of interest for a particular diagnosis and accordingly transduce a signal. Paired with peripheral devices for signal processing, POC biosensors cut detection time to minutes and break the barrier of expertise in medical diagnostics. Furthermore, panels of biosensors can be used to enhance diagnostic capabilities. For example, Tonic et al. Were able to design a sensor capable of detecting 5 types of cytokines in order to distinguish bacterial and non-bacterial forms of sepsis. Thus, it is our objective in this lab to optimize biosensors' geometry, size, spacing, and orientation for combinatorial use. The panel designed in this study will give rise to a modular methodology entitled as RAPID, or a raster and prototype interface design model that can be used to create a benchmark criteria for prototyping biosensors in the future. To conduct the simulation, first 16 design iterations for a 2x2 sensor platform were designed, as can be seen in Figure 1. Each design featured 2 3-electrode systems and 2 2-electrode systems, but varied in shape, size, spacing, and orientation. As demonstrated in Figure 2, gold is assigned to the electrode domain, while phosphate buffered saline was assigned to the electrolyte domain in order to simulate the sensor being submerged in a liquid electrolyte. 10 millivolts of potential were applied at the working electrodes, while counter electrodes were grounded and von Neumann boundaries were applied to the reference electrode. The simulation offers results through current density and potential distribution plots, as well as current density streamline plots. Line plots were derived from the current density and potential distribution plots to analyze current density from the working to counter electrode and potential from the working to reference electrode. Preliminary results from the 16 iterations demonstrated a perceivable difference between the current density streamline plots of iterations with a large counter electrode versus large reference electrode. As iterations with large reference electrode displayed significant crosstalk between electrode systems within the panel, they were eliminated, as is displayed in Figure 3. The remaining 8 designs were examined based on current density between the working and counter electrodes. As Figure 4 demonstrates, iterations featuring straight geometries were eliminated as they displayed a tendency towards fringe effects, causing unstable current density readings rather than a uniform gradient decay shown in the curved geometry counterparts. The last 4 electrode designs were judged based on delta J, or the change in current density between working and counter, and delta phi, or the change in potential between working and reference electrodes, as can be seen in Figure 5. While delta phi values were mostly similar among the iterations, the design featuring a curved geometry, 1 by 1 by 2 area ratios, and 2 centimeters of spacing between the working and counter electrode, and oppositely oriented 3-electrode systems arose as the optimal biosensor design, as it featured the highest delta J value. This can be seen in Figure 5. Lastly, we would like to conclude by emphasizing the significance of finding combinatorial sensors which feature both 2-electrode and 3-electrode systems. While 2-electrode systems measure non-Faraday current, in some applications it may be advantageous to filter non-Faradaic and Faradaic signals using a 3-electrode system. RAPID establishes a benchmark for biosensor prototyping, which can feature both simpler 2-electrode systems and more complex 3-electrode systems, all in one panel sensor. Lastly, we would like to acknowledge our references listed on the poster and give a special thanks to Tonic et al. For providing photos of their multiplex sepsis sensor to once again demonstrate the importance of combinatorial biosensors. Thank you for listening.